Database in Hibernate. Now we are focusing on database. Database, also called electronic database, any collection of data or information that is specially organized for rapid search and retrieval by a computer. Databases are structured to facilitate the storage, retrieval, modification, and deletion of data in conjunction with various data processing operations. A database management system, DBMS, extracts information from the database in response to queries. Here you can see how Hibernate works. Um, um, at the heart of every interaction between your code and the database lies the Hibernate session. The heart of any Hibernate application is in its configuration. There are two pieces of configuration required in any Hibernate application. One to create the database connection, and the other creates the object to table mapping. Here you can see .cfg.xml. This file is connected to Hibernate configuration for database 1. Loaded to create is passed from .cfg.xml file to Hibernate configuration data for database 1. Hibernate configuration for database 1 is connected to database 1. And here .cfg.xml is connected to class 1 hmb.xml and other similar files. Here defines the database specific settings and groups, HBMs for a given database. .cfg.xml is connected to Hibernate configuration for database 2, and loaded to create is passed from .cfg to .cfg.xml to Hibernate configuration for database 2, and Hibernate configuration for database 2 is connected to database 2. And here work with multiple databases. And Hibernate configuration for database 2 is connected to factory, and configuration object is used to create here, and single factory is singleton per database, and factory is connected to session, and there's a bridge between among tables and classes and session. Here you can see Hibernate ORM and Hibernate OGM. If you take MongoDB as NoSQL database here, MongoDB does not require following ACID properties, and hence do not support the transaction. Hibernate OGM mitigate its lacking by queuing changes before committing them. Hibernate OGM also recommends using in transaction demarcation with no rollback option. Perhaps this is the reason why bootstrapping through JTA is suggested. because of JPA is an inherently relational API, so be prepared for you to run into these aspects. First, JPA is not supporting a plethora of the features MongoDB exposes: geopartial functionality, upserts, etc. You are going to need a custom extension for that, in which minimizes the benefit of using JPA in the first place. And number two, a plethora of stuff available in JPA doesn't make any sense in MongoDB non-relational world, and won't be supported. Transactions, what's a join column supports supposed to be in MongoDB. The former not bring available a pretty dangerous actually. What's supposed to happen if a JPA developer calls transaction.rollback? Strictly speaking, you can't implement JPA 100% by definition, and most of the self-proclaimed JPA implementations for NoSQL are basically providing a tiny subset of JPA. Some of the annotations for mapping some of the entity manage API. And number three, simply switching the store behind an object model is fallacy to especially NoSQL stores are built in a way to favor certain data structures. MongoDB is good for documents. Neo4j is highly interconnected data. That means that you will model the domain code and the converters differently based on what you store you actually use. Switching stores arbitrarily will lead you to reduce your domain model to a least common denominator and basically make less use of the features that might you select the store in the first place. Here you can see Hibernate ORM here, and application, then Hibernate ORM, then JNDI, JDBC layer, JTA, and these are interact with SQL database, and SQL statements are passed to SQL database, and results from SQL database. Here you can see Hibernate OGM, application, Hibernate ORM, Hibernate OGM, data store provider, grid dialect, and these are interacting with NoSQL database. Here you can see the general architecture of Hibernate OGM. Hibernate OGM is really made possible by the reuse of a few key components. Hibernate ORM for JPA support, Hibernate's search for indexing and query purposes, the NoSQL drivers to interact with underlying data store, Infinispan's losing directory to store indexes in Infinispan itself or in many other NoSQL using Infinispans right through cache stores, Hibernate OGM itself. Hibernate OGM reuses as much as possible from Hibernate ORM infrastructure. There's no need to rewrite an entirely new JPA engine. Persisters and loaders two interfaces used by Hibernate ORM have been rewritten to persist data in the NoSQL store. This implementation are the core of Hibernate OGM. The particulars between NoSQL stores are abstracted by the notion of data store provider and data grid. Data store provider abstracts how to start and maintain a connection between Hibernate OGM and the data store. Grid dialect abstract how itself, including association, is persisted. Other than these, all the create, read, update, delete, CRUD operations are implemented by the Hibernate ORM engine. Object hydration and dehydration, cascading, lifecycle, etc. As if today, 4 data store providers are implemented: a map-based data store provider for testing, an InfiniSpan-based data store provider for persist your entities in InfiniSpan, Ncache-based data store provider to persist your entities in Ncache, a MongoDB-based data store provider to persist data in a MongoDB database. To implement JPQL queries, Hibernate OGM passes the JPQL string and calls the appropriate translator functions. To build a native query. If the query is too complex, the native capabilities of the NoSQL store, the tied query engine is used as the an intermediary engine to implement the missing features, typically joins between entities, aggregation. Finally, if the underlying engine does not have any query support, Hibernate Search is used as an external query engine. Hibernate OGM best work in a JTA environment. The easiest solution is to deploy it on a Java EE container. Alternatively, you can use a standalone JTA transaction manager. Here you can see application. Object model is inside the application, and application is connected to JPA or Hibernate native APIs, and it's interact with JPA or Hibernate native APIs. JPA or Hibernate native API, Hibernate core, Hibernate ORM core, Hibernate OGM core, data store provider, and grid dialect query engine are in Hibernate OGM. JPA or Hibernate native APIs are connected to Hibernate ORM core. Basically, they are interacting with ORM, Hibernate ORM core, and Hibernate ORM core is connected to Hibernate OGM core. Delegates persistence load queries to Hibernate OGM core. Hibernate OGM core delegates data store CRUD operations to data store provider and grid dialect. Data store provider and grid dialect interacts with data store here with NoSQL data store. Hibernate OGM core delegates queries to JPQL parser. JPQL parser, data store query translator, and tied query engine and connectors are inside query engine. And JPQL parser delegates simple queries to data store query translator. JPQL parser delegates complex queries to tied query engine and connectors. Tied query engine and connectors transform in a simpler data store supported queries to data store query translator. Data store query translator executes native queries, and it is connected to SQL data store. Here you can see a separate database in multi-tenant approaches. Each tenant data is kept in a physically separate database instance. JDBC connection would point to which point specifically to each database, so any point would be per tenant. A general application approach here would be to define a JDBC connection pool per tenant and to select the pool to use based on the tenant identifier associated with the currently logged in user. Here you can see application is connected to databases. Here you can see a separate schema in multi-tenant approaches. Each tenant data is kept in a distinct database schema. There are two different ways to define JDBC connections here. Connection could point to specifically to each schema as we show in the separate database approach. This is an option provided that the driver supports naming distinct default schema in the connection URL or if the pooling mechanism supports the naming schema for use its connections. Using this approach, we would have a distinct JDBC connection pool per tenant, where the pool to use would be selected based on the tenant identifier associated with the currently logged in user. Connections could point to database itself using the default schema, but the connections would be altered using SQL set schema or similar command. Using this approach, we would have a single JDBC connection pool for use to service all tenants, but before using connection it would be altered to reference schema name the current tenant identifier associated with the currently logged user. Here you can see application is connected to databases. Partition discriminator data in multi-tenant data approaches. The all data is kept in a single database schema. The data for each tenant is partitioned by the use of partition value or discriminator. The complexity of this discriminator might range from simple column value to a complex SQL formula. Again, this approach would use a single connection pool service to all tenants. However, in this approach, the application needs to alter each and every SQL statement to send to database to reference the tenant identifier discriminator. Here, application is connected to the database. As an example, we can configure the database connection. This segment is from hibernate.cfg.xml. To create a connection to a database, Hibernate must know the details of our database tables, classes, and other mechanics. This information is ideally provided as XML file, usually named hibernate.cfg.xml, or as a simple text file with name value pairs, usually named hibernate.properties. Here connection URL indicates the URL to which we should be connected, and driver underscore class represent the relevant driver class to make the connection, and dialect indicates which database dialect we are using. MySQL in this case, and if you are following the hibernate.properties file approach, note that all the properties are prefix with Hibernate and follow pattern Hibernate asterisk properties, for instance. We can consider this one as example 2 for Hibernate OGM. This is in persistent.xml. So here we have to define data store details in the Hibernate persistent.xml. The value of the attribute transaction dash type as an JTA. This implies that we want a JTA entity manager from the entity manager factory, and provider, which is Hibernate OGM persistence for Hibernate OGM. Additional details related to DB. These typically vary between different data sources. The configuration assumes MongoDB is running and accessible on defaults. If this is not the case, we can always provide details as necessary. And as an example 3, we can consider this one in hibernate.properties file. Here connection hibernate.connection.ur indicates the URL to which we should be connected. Driver class represents the relevant driver class to make a connection, and the dialect indicates which database dialect we are using, MySQL in this case. If you are following the hibernate.properties file approach, note that all the properties are prefixed with Hibernate and follow a pattern Hibernate.*properties, for instance. As an example 4, we can consider this code segment. Here the class configuration. An instance of a configuration allows the application to specify properties and mapping documents to be used when creating a session factory. Usually an application will create a single configuration, build a single instance of session factory, and then instantiate sessions in a thread servicing client requests. The configuration is meant only as a initialization time object. Session factories are immutable and do not retain any association back to the configuration. The class configuration is in org.hibernate.cfg. As an exception, now we are considering columns index. Here is at index mapping example. The at index annotation is used by the automated schema generation tool to create a database index. Considering the following entity mapping, Hibernate generates the index when creating a database schema. Getter and setters omitted for brevity. Now we are considering connection provider in database access. Hibernate will internally determine which connection provider to use based on the following diagram. Interface connection provider in package org.hibernate.engine.jdbc.connection.spi, a contract for obtaining JDBC connections and optionally for pooling connections. As an ORM tool, probably the single most important thing you need to tell Hibernate is how to connect to a database so that it may connect on behalf of your application. This is ultimately the function of the org.hibernate.engine.jdbc.connection.spi connection provider interface. Hibernate provides some out-of-box implementation of this interface. Connection provider is also an extension point, so you can also use the custom implementation from third parties or written yourself. The connection provider is defined by the hibernate.connection.connection provider underscore class setting. Generally speaking, applications should not have to configure the connection provider explicitly if using one of the Hibernate provided implementation. Hibernate will internally determine which connection provider to use based on the following algorithm. 1. If Hibernate connection provider class is set, it takes precedence. 2. Else if hibernate.connection.dataSource is set using data sources. 3. Else if any settings prefixed by hibernate.3cp0 is set using 3c3p0. 4. Else if any setting prefixed by hibernate.proxol is set using proxol. 5. Else if any setting prefixed by hibernate.hikari is set using hikari cp. 6. Else if any setting prefixed by hibernate.vibu is set using vibu.dbcp. Else if any settings prefixed by hibernate.agrol is set using agrol. Else if hibernate.connection.url is set using Hibernate's built-in and unsupported pooling. Else user provided connections. Now we are considering using data sources. Hibernate can integrate with javax.sql.datasource or for obtaining JDBC connections. Application would tell Hibernate about the data source via the required hibernate.connection.dataSource settings, which can either specify a JNDI name or would reference an actual data source instance. For Jakarta persistent applications, note that hibernate.connection.dataSource corresponds to jakarta.persistence.jta datasource or jakarta.persistence.none.jta datasource. The data source connections, the data source connection provider also optionally accepts the hibernate.connection.username and hibernate.connection.password. If specified, the data source #get connection string username string password will be used. Otherwise, no args form is used. Now we are considering driver configuration. Here, hibernate.connection.driver_class, the name of the JDBC driver class to use. Here we are considering using C3P0 C3P0.minsize or C3P0.minpoolsize, the minimum size of the C3P0 pool. Now we are considering using existing proxol pools in using proxol controlled by the hibernate.proxol.existing_pool setting. If set to true, this connection provider will use the already existing proxol pool by alias as indicated by the hibernate.proxol.pool_alias settings. Now we are considering using Hikari CP Hibernate.connection.driver underscore class map to Hikari's driver class name setting. Now we are considering using Vibu DBCP Hibernate.connection.driver underscore class map to Vibu's driver class name setting. Now we are considering using a role Hibernate.connection.driver underscore class map to a role's driver class name setting. Now we are considering using Hibernate's built-in and unsupported pooling. The built-in connection pool is not supported for use in production and systems. So now we are considering user-provided connections. It is possible to use Hibernate by simply passing a connection to use to the session when the session is opened. This usage is discouraged and not discussed here. Now we are considering connection provider support for transaction isolation setting. The value for Hibernate.connection.isolation can be specified in one of three formats. All of the provided connection provider implementations other than data source connection provider support consistent settings of transaction isolation for all connections. The connections obtained from the underlying pool. The value for Hibernate.connection.isolation can be specified in one of three formats. The integer value accepted at the JDBC level, the name of the java.sql.connection constant field representing the isolation you would like to use. For example, transaction underscore repeatable underscore read for java.sql.connection hash transaction underscore repeatable underscore read. Note that this is only supported for JDBC standard isolation level, not for isolation level specific to a particular JDBC driver. A short name version of the java.sql.connection constant field without the transaction underscore prefix. For example, repeatable underscore read for java.sql.connection hash transaction underscore repeatable underscore read. Again, this is only supported for JDBC standard isolation levels, not for isolation level specific to particular JDBC driver. Now we are considering connection handling. Here, immediate underscore acquisition underscore and underscore hold. The connection will be acquired as soon as the session is opened and held until the session is closed. The enum constant public static final physical connection handling mode immediate underscore acquisition underscore and underscore hold. The connection will be acquired as soon as the session is opened and held until the session is closed. This is the only valid combination including immediate acquisition of the connection. This is in the package connection, and this is in the enum physical connection handling mode. Enumerates valid combination of connection acquisition mode and connection release mode, which is the enum is in package octahibernate.resource.jdbc.spi. There are other strategies like delayed acquisition and hold, delayed acquisition and release after statement, delayed acquisition and release after transaction. Now we are considering user provided connections. If the current session was created using the session builder and the JDBC connection was provided via the session builder hash connection method, then the user provided connection is going to be used and the connection handling mode will be immediate underscore acquisition underscore and underscore hold. The method session builder connection adds a specific connection to the session points. This is in the interface session builder and which is in the package org.hibernate. And therefore, for the user provided connection, the connection is acquired right away and held until the current session is closed without being influenced by the Jakarta persistence or Hibernate transaction context. Now we are considering database dialect. Here you can see cache 71 support for the cache database version 2007.1. For some reason it is not able to determine proper one, or for you want to use a custom dialect, you will need to set the hibernate.dialect settings for change set the dialects. Here we are considering dialect cache 71, and with regarding class dialect represent a dialect of SQL implemented by a particular RDBMS. Every class of this class implements support for the certain dialect database platform. For example, PostgreSQL dialect implements the support for PostgreSQL, and MySQL dialect implements support for MySQL. The class dialect is in package org.hibernate.dialect. Now we are considering overview in Spatial. Supported databases are Oracle 10G, 11G, Postgres, SQL, PostgreGIS, MySQL, Microsoft SQL Server, DB2, Cockroach DB, and H2 or GeoDB. The Hibernate Spatial was originally developed as a generic extension to Hibernate for handling geographic data. Since 5.0, Hibernate Spatial is now part of the Hibernate ORM project, and it allows you to deal with geometric data in standardized way. Hibernate Spatial provides a standardized cross-database interface to geometric data storage and query functions. It supports most of the functions described by the OGC in simple feature specification. Supported databases are Oracle 10G, 11G, PostgreSQL, PostGIS, MySQL, Microsoft SQL Server, DB2, Cockroach DB, and H2 or GeoDB. Spatial data types are not part of Java standard library, and they are absent from JDBC specification. Over the years, JTS has emerged as a de facto standard to fill this gap. JTS is an implementation of simple feature specification, SFS. Many databases, on the other hand, implement the SQL hash or part 3 spatial data specification, related but border specification. The biggest difference is SFS is limited to 2D geometries and the projected pane, although GTS support 3D coordinates, where SQL or support 2, 3 or 4 dimensional coordinate spaces. Hibernate Spatial supports two different geometric modes, JTS and GeoLet GOM. As already mentioned, JTS is the de facto standard, and GeoLet GOM, also written by lead developer of Hibernate Spatial, is more recent library that support many features specified in SQL or but not available in JTS, such as support for 4D geometries and support for extended WKT or WKB formats. GeoLet GOM also implement encoders, decoders, or for the database native types. GeoLet GOM has good interoperability with JTS, converting a GeoLet geometry to a JTS geometry. For instance, doesn't require copying of coordinates. It also delegates spatial processing of JTS. Whether you use JTS or GeoLet GeOM, Hibernate Spatial maps the database spatial types to your geometry model of choice. It will, however, always use GeoLet GeOM to decode the database native types. Hibernate Spatial also make the number of spatial functions available in SQL and in the criteria query API. These functions are specified in the both SQL and or as SFS, and are commonly implemented in the database with spatial support. Now we are considering dependency in configuration. Here, Maven dependency. You need to include Hibernate hash spatial dependency to your build environment for Maven you need to add following dependency. Note that all databases support all functions defined by not all databases support all functions defined by Hibernate Partial. The table now we are considering DB2 in database nodes. One way to do is to copy this statement into a file such as kt.sql and execute it in the db2 command window with the command such as db2-tvf ewkt.sql. The db spatial dialect supports the spatial extension of db2 LUW database. The dialect has been tested with db2 LUW 11.1. The dialect does not support db2 for Z or OS or db2 column oriented databases. In order to use db2 Hibernate spatial capabilities, it is necessary to first execute the following SQL statement, which will allow db2 to accept extended well-known text ewkt data and return ewkt data. The one way to do is to copy these statements into a file such as ewkt.sql and execute it in the db2 command window with a command such as db2 -tvf ewkt.sql. Now we are considering types. Here types mapping. Hibernate Spatial comes with different types. It's sufficient to declare the property as either JTS or geometry, and Hibernate Spatial will map it using relevant type. Here is the example using JTS. Now we can now treat spatial geometries like any other type. Here's creating a point. Spatial dialects define many query functions that are available in both HQL and JPQL queries. Below we show how we could use the within function to find all the objects within given spatial extent or window. Getters and setters are omitted for brevity. Now we are considering multi-tenancy. What is multi-tenancy? The term multi-tenancy is applied to software development to indicate an architecture in which a single running instance of an application simultaneously serves multiple client tenants. This is highly common in SaaS solutions, isolating information, data customizations, etc. pertaining to various tenants is a particular challenge in these systems. This includes the data owned by each tenant stored in the database. It is this last piece, sometimes called multi-tenant data, that we will focus on. Now we are considering multi-tenancy in Hibernate, specifying tenant identifier from a session factory. Method session builder dot tenant identifier string tenant identifier define the tenant identified to be associated with the open session. This is in the interface session builder, which is in the package org.hibernate. Using Hibernate with multi-tenant data comes down to both an API and then integration pieces. As usual, Hibernate strives to keep the API simple and isolated from any underlying integration complexities. The API is really just defined by passing the tenant identifier as part of the opening and session. Now we are considering at tenant ID. At tenant ID usage example is here. The annotation type tenant ID identifies a field of an entity that holds a tenant ID in a discriminator based multi-tenancy. This is in the package org.hibernate.annotations. For the partition data approach, for each entity representing partitioned data must declare a field annotated with a tenant ID. The tenant ID field is automatically populated by Hibernate when an instance is made persistent. Now we are considering a multi-tenant connection provider. A multi-tenant connection provider implementation here. The multi-tenant connection provider interface multi-tenant connection provider, a specialized connection provider contract used when the application is using multi-tenancy support requiring tenant-aware connections. The interface multi-tenant connection provider is in package org.hibernate.engine.jdbc.connection.spi. The abstract multi-tenant connection provider class, the basic support for multi-tenant connection provider implementation using individual connection provider instances per tenant behind the scene. When using either a separate database or separate schema approach, Hibernate needs to be able to obtain connections in a tenant specific manner. That is the role of multi-tenant connection provider. Multi-tenant connection provider contract. Application developers will need to provide an implementation of this contract. Most of the methods are extremely self-explanatory. Only ones which might not be get any connection and release any connection. It is important to note that that these methods do not accept tenant identifier. Hibernate uses these methods during startup to perform various configuration, mainly via SQL, java.sql.database metadata object. The multi-tenant connection provider to use can be specified in a number of ways. Use the hibernate.multi-tenant multi_tenant_connection_provider setting. It could name multi-tenant connection provider into instance, a multi-tenant connection provider implementation class reference to a multi-tenant connection provider implementation class name. Pass directly to org.hibernate.boot.registry.standard service registry If none of above options match, but the settings do specify hibernate.connection.data source value, Hibernate will assume it should use the specific data source based multi-tenant connection provider IMPL implementation, which works on a number of pretty reasonable assumptions when running inside an app server and using one java x.sql.data source per tenant. The following example portrait multi-tenant connection provider implementation that handle multiple connections, handle multiple connection providers. The multi-tenant connection provider implementation is here. For the configurable multi-tenant connection provider can be set up as follows. Multi-tenant connection provider usage example. Here a multi-tenant connection provider usage example. When using multi-tenants, it's possible to save an entity with same identifier across different tenants. Now we are considering current tenant identifier resolver. There is two situations where the current tenant identifier resolver is used. Interface current tenant identifier resolver in package org.hibernate.context.spi. A callback registered with the session factory that is responsible for resolving the current tenant identifier. The org.hibernate.context.spi.current session identifier resolver is a contract for Hibernate to be able to resolve with what the application considers the current tenant identifier. The implementation to use can be either passed directly to configuration via its set current tenant identifier resolver method, or be specified via hibernate.tenant_identifier_resolver setting. There are two situations where current tenant identifier resolver is used. First situation is when the application is used the org.hibernate.context.spi.current session context feature in the conjunction with multi-tenancy. In the case of the current session feature, Hibernate will need to open a session if it cannot find the existing one in scope. However, when a session is opened, the multi-tenancy environment, the tenant identifier has to be specified. This is where the current tenant identifier resolver comes into play. Hibernate will consult the implementation you provide to determine the tenancy identifier to use when opening the session. In this case, it is required that a current tenant identifier resolver is supplied. The other situation is when you do not want to explicitly specify the tenant identifier all the time. If the current tenant identifier resolver has been specified, that Hibernate will use it to determine the default tenant identifier to use when opening the session. Additionally, the current tenant identifier resolver implementation returns true for its validate existing current sessions method. Hibernate will make sure any existing sessions that are found in the scope have a matching tenant identifier. This capability is only pertinent when the current tenant identifier resolver is used in current tenant settings. Now we are considering caching. Multi-tenancy support for Hibernate works seamlessly with the Hibernate second level cache. The key used to cache data encodes the tenant identifier. Currently, the schema will export. The schema export will not really work with multi-tenancy. Now we are considering multi-tenancy Hibernate session configuration. The register connection provider method. The register connection provider method used to defining the tenant specific context. When using multi-tenancy, you might want to configure the each tenant specific session differently. For instance, each tenant could specify different time zone configuration. Here they are registering the tenant specific time zone information. The register connection provider method is used to define the tenant specific context. In our example, the tenant specific context is held in the connection provider map and time zone tenant map. Now when building Hibernate session, aside passing the tenant identifier, we could also configure the session to use the tenant specific time zone. Here the Hibernate session can be configured using tenant specific context. So if we set the use tenant time zone parameter to true, Hibernate will persist the timestamp properties using tenant specific time zone. As you can see the following example here, timestamp is successfully retrieved even if the currently running JVM uses different time zone. However, behind the scene, we can see that Hibernate has saved the create on property in the tenant specific time zone. Following example shows that timestamp was saved in the UTC time zone, hence offset displayed in the test output. Here the with the use tenant time zone, property to set to false if the timestamp is fetched in the tenant specific time zone. Notice that for Eastern European time zone is the time zone offset was 2 hours when the test was executed. Here the persisting part now we are considering portability basics in database portability considerations. One of the selling point of Hibernate and the really object relational mapping as a whole is the notion of database portability. This could mean an internal IT user migrating from one database vendor to another, or it could mean a framework for deployable application consuming Hibernate to simultaneously target multiple products by their users. Regardless of the exact scenario, the basic idea is that you want Hibernate to help to run you against any database, any number of databases without changes to your code, ideally without any changes to the mapping data metadata. Now we are considering dialect. The org.hibernate.dialect.dialect. The first line of portability for Hibernate is the dialect, which is specialization of the org.hibernate.dialect.dialect contract. A class dialect represent the dialect of SQL implemented by a particular RDBMS. Every subclass of this class implements support for a certain database platform. For example, PostgreSQL dialect implements support for PostgreSQL and MySQL dialect implements the support for MySQL. A dialect encapsulate all the differences in how Hibernate must communicate with the particular database to accomplish some task, like getting a sequence value for structuring a select query. Hibernate bundles a wide range of dialects for many of the popular databases. If you find that your particular database is not among them, it is not terribly difficult to write your own. Now we are considering dialect resolution. Starting with version 3.3, Hibernate has far more powerful way to automatically determine which dialect to be used by relying on a series of delegates which implement the org.hibernate.dialect.resolver.dialect.resolver, which define only a single method. Originally, Hibernate would always require that users specify which dialect to use. In the case of users looking at the simultaneously target multiple databases with their build, that was problematic. Generally, this required the users to configure the Hibernate dialect or defining their own method of setting that value. Starting with version 3.2, Hibernate introduced a notion of automatically detecting the dialect to use based on the java.sql.database metadata obtained from the java.sql.connection to that database. This was much better, except that the resolution was limited to databases Hibernate know about ahead of time and was in no way configurable or overridable. Starting with version 3.3, Hibernate has far more powerful way to automatically determine which dialect to be used by relying on series of delegates which implement the Hibernate.dialect.resolver.dialect.resolver, which defines only one single method. Basic contract here is that the resolver understands the given database metadata when it returns the corresponding dialect. If it's not returned null, if not, it returns null and process continues to the next resolver. Signature also identified the Hibernate Hibernate.exception.jdbc connection exception as possibly being thrown. The connection exception here is interpreted to imply a non-transient, also known as non-recoverable connection problem, and is used to indicate an immediate stop to resolution attempts. All other exceptions result in warning and continuing on the next resolver. The cool part of these resolvers is that users can also register their own custom resolvers which will be processed ahead of built-in Hibernate ones. This might be useful in a number of different situations. It allows easy integration for auto detection of dialects beyond those shipped with Hibernate itself. It allows you to specify to use the custom dialect when a particular database is recognized. To register one or more resolvers, simply specify them separated by commands, tabs or spaces using Hibernate.dialect_resolvers configuration settings. Now we are considering identifier generation. There are specifically two bundled enhanced generators. The class sequence style generator in package org.hibernate.id.enhance generates identifier values based on sequence style database structure. Variations range from actually using a sequence to using a table to mimic a sequence. These variations are encapsulated by the database structure interface internally. When considering portability between databases, another important decision is selecting the identifier generation strategy you want to use. Originally, the Hibernate provided a native generator for this purpose, which was intended to select between sequence, identity, or table listed depending on the capability of underlying database. However, in insidious implication of this approach comes when they're targeting some databases which support identity generation in some which do not. Identity generation relies on this SQL definition of an identity or auto increment column to manage the identifier value. It is what is known as the post insertion generation strategy because the insert must actually happen before we know the identifier value, because Hibernate relies on this identifier value to uniquely reference entities within a persistent context. It must then issue the insert immediately when the user requests that identity be associated with the session, like via save or persist, regardless of the current transaction semantics. Hibernate was changed slightly once implications of this were better understood. So now insert could be delayed in cases where this is feasible. The underlying issue is that the actual semantics of the application itself changes these cases. Starting with version 3.2.3, Hibernate comes with a set of enhanced identifier generators targeting portability in which much different way. This specifically bundled with enhanced generator org.hibernate.id.enhance.identity sequence style generator, and other one is org.hibernate.id.enhance.table generator. The idea behind these generators is to plot the actual semantics of the identifier value generation to the different databases. For example, org.hibernate.id.enhance.sequence style generator mimics this behavior of a sequence on databases which do not support sequence by using a table. Now we are considering database functions. There are even way for a program to contribute its own function definition. Here the function type applied to an identification variable evaluates to the identity name of the reference entity. This is mainly useful when dealing with entity inheritance hierarchies. HQL now provide a large set of functions which are portable between databases. Using parameter instead of literal entity type. Now we are considering database connection properties in configurations. Here hibernate.connection.driver underscore class or jakarta.persistent.jdbc.driver, for example, postgresql.driver names the JDBC driver class name. Now we are considering Hibernate internal connection pool options. Hibernate.connection.initial underscore pool underscore size, for example, one default value, minimum number of connections for the built-in Hibernate connection pool. Well, we can consider this caused by java.sql SQL exception ORA-12899 value too large for column JBPM dot case fields dialog dot item value. As an error example, we can consider this could not get list of tables from database, probably a JDBC driver problem. This is now this is the end of my presentation. Thank you very much for watching it.